Section: Introduction and Related Work. In this section, we explore regression, a key statistical method that helps us understand the relationship between a metric and a set of features. This technique is vital across various fields for making predictions and uncovering data relationships. Traditionally, regression relies on manually crafted features or specific domain knowledge. However, with the rise of large language models, LLMs, we question whether we can perform regression using free-form text instead. Previous research has mainly focused on LLM-based regression through decoding, which involves generating numerical predictions by sampling tokens. Some studies have looked at fully accessible models that can be fine-tuned, while others have examined closed-source models like GPT-4 using in-context learning. A less explored area is the use of LLM embeddings, fixed vector representations from pre-trained language models. These embeddings are commonly used in applications like semantic similarity but have not been thoroughly researched for direct regression use, apart from specific cases like Bayesian optimization. Unlike decoding-based methods, embedding-based regression allows for cost-effective training with customizable layers, such as multi-layer perceptrons, MLPs. However, we note that when we express simple functions using high-dimensional embeddings, unexpected issues can arise, necessitating careful analysis. Additionally, LLMs are primarily trained for token generation, not specifically for embedding-based regression, so we need to investigate how they behave in this context. Our findings reveal that LLM embeddings are dimensionally robust, meaning they perform well even with high-dimensional data, unlike traditional representations. They also maintain smoothness and continuity over numeric formats, which supports effective regression with MLPs. We find that factors influencing language understanding, such as model size and input formatting, have more complex effects on regression performance and do not always lead to better results. In our methodology, we define a regression task as consisting of a scalar-valued function over an input space, with training and test data provided. Our goal is to make accurate predictions on test points, typically evaluated using metrics like mean squared error. We assume that features come from an embedding function that transforms input into a fixed dimensional representation. We interchangeably use features and embedding, as traditional methods often rely on defined feature engineering for tabular data. The process for language models involves tokenizing input, obtaining a soft prompt, applying a transformer, and pooling to a fixed dimensional vector. We can then attach an MLP predictor and train it similarly to traditional methods. The main difference lies in the input representation, whether we use traditional or LLM-based embeddings. We aim to understand how each step in the LLM process contributes to the final regression outcome, exploring variations in the approach in detail. Section Summary. In this section, we explore the potential of using large language model, LLM, embeddings for regression tasks, highlighting their robustness in high-dimensional data and their ability to maintain performance compared to traditional methods. We also discuss the differences in feature representation between traditional and LLM-based approaches, emphasizing the need for further analysis on how various components of LLM embeddings contribute to regression outcomes. Section: Modeling. In this section, we focus on modeling to ensure fairness in our comparisons. We utilize the same MLP prediction head, which consists of two hidden layers with ReLU activation, the same loss function based on mean squared error, and the same normalization method for our outputs, regardless of whether we are using LLM or traditional embeddings. It is important to note that the dimensions of these embeddings may differ, which we denote as D for LLM and D for traditional, with LLM typically having a much larger dimension. To validate our findings across various language model families, we benchmark both the T5 and Gemini 1.0 models, which differ in architecture, vocabulary size, and embedding dimensions. We adopt average pooling as the standard method for aggregating outputs from transformers, ensuring that the embedding dimension for LLM matches the output feature dimension after processing. For our regression tasks, we start with synthetic, closed-form objective functions to create controlled studies. These functions are derived from the black box optimization benchmarking suite. To clarify terminology, we refer to the intrinsic dimension of an objective function as degree of freedom, DOF, which depends on input coordinates that range from -5 to +5. This setup allows us to explore a wide range of both convex and non-convex landscapes. We also include real-world regression tasks that reflect challenges faced in practical applications, using data from Google Vizier, which optimizes various systems at Google. We categorize these tasks into 4 families, each containing at least 50 similar regression tasks. AutoML for automating machine learning pipelines, Init2Winit for learning rate scheduling in image classification, XLA for tuning the accelerated linear algebra compiler, and L2DA for improving hardware performance. In real-world tasks, parameters can be continuous or categorical, and we define the DOF based on the number of parameters. For synthetic objectives, the traditional dimension equals the DOF, but for real-world tasks with categorical parameters, the traditional dimension exceeds the DOF due to one-hot encodings. We gather data by sampling pairs of inputs and outputs for synthetic tasks or using existing offline data for real-world tasks, applying a standard train validation test split. Given the varying scales of metrics across tasks, we avoid aggregating results based on scale-dependent metrics like mean squared error. We found that the choice of regression metric did not significantly impact our comparisons, as they were all strongly correlated. Therefore, we report the Kendall-Tau ranking correlation by default, which ranges from 0 to 1 and can be aggregated across different tasks. In our experimental results, we first demonstrate that LLM embeddings often provide better representations in high-dimensional spaces compared to traditional methods. We show that for certain functions, LLM embeddings maintain performance across varying degrees of freedom, while traditional methods like XGBoost and MLPs struggle as the DOF increases. Although this trend is not universal, it holds true for most functions in the BBOB suite, and we further support this finding with real-world task results. Overall, we observe that regressions using LLM embeddings tend to outperform traditional methods, especially in tasks with higher degrees of freedom. Section Summary. In this section, we outline our modeling approach, ensuring fairness by using a consistent MLP prediction head and loss function across different representations, while benchmarking performance on both synthetic and real-world regression tasks. We demonstrate that LLM embeddings generally outperform traditional methods, particularly in high-dimensional regression scenarios, although this trend is not universal across all functions. Section: LLM Embedding Smoothness. In this section, we explore the smoothness of embeddings from large language models, LLMs. Due to the way tokenization works, it's not clear if LLM embeddings are continuous in their space. For instance, if we tokenize by characters, the numbers 1.234 and 1.567 may seem close numerically, but they are far apart in terms of tokens since they share no common parts. Understanding continuity and smoothness is important for how well neural networks generalize and their vulnerability to adversarial attacks. We can define smoothness in regression using a concept called Lipschitz continuity, which suggests that similar inputs should yield similar outputs. We express this with a Lipschitz factor that measures the difference in outputs relative to the difference in their representations. It's important to note that the input space itself doesn't have a clear distance metric. Traditionally, we've used Euclidean distance based on standard embedding methods. However, our earlier results indicate that these traditional methods may not always be the best for regression tasks. To analyze the continuity of an embedding with respect to our offline data, we introduce a normalized Lipschitz factor distribution, NLFD. We normalize each embedding vector to have a mean of 0 and a variance of 1 across our dataset. For each data point, we find its nearest neighbor in the embedding space and calculate the Lipschitz factor. We adjust these factors to account for different embedding dimensions. Our findings show a strong inverse relationship between the skewness of the NLFD and regression performance. Specifically, When the LLM embedding outperforms the traditional one, its Lipschitz factors tend to cluster closer to 0. To compare the NLFDs of the LLM and traditional embeddings, we compute a z-score based on the differences in their distributions. This allows us to observe how gaps in smoothness relate to regression performance. Our results indicate a high correlation between these gaps and performance across various models and tasks. We also investigate whether the LLM embeddings are aware of distance, meaning if 2 points that are close in traditional space are also close in the LLM space. Since there's no definitive measure of closeness, we use the traditional embeddings as a reference. Instead of sampling uniformly in high-dimensional space, we sample points from spheres of increasing distance from a reference point. Our analysis shows that distances in the LLM embedding space correlate with traditional measures, although they may be warped in a way that benefits regression. Next, we examine how various factors related to LLMs affect regression performance. A common belief is that larger models perform better, but recent evidence shows that smaller models can outperform larger ones due to differences in their training processes. Our observations indicate that while T5 models generally improve with size, the Gemini models show more variability, suggesting that their training methods differ significantly. We also question whether language understanding contributes to performance in numeric regression tasks. By comparing the performance of a pre-trained model with a randomly initialized one and using vocabulary embeddings, we find that the pre-trained model usually performs best. However, in some cases, like AutoML, the improvement is minimal, indicating that pre-trained models don't always enhance regression performance. We further analyze how the representation of features affects performance. For most tasks, omitting feature names doesn't significantly impact results, although some tasks do benefit from including them. Interestingly, even when using numeric-only inputs, applying forward passes with pre-trained models still improves regression, despite the lack of scientific data in their training sets. Finally, we observe that having more training data reduces the performance gaps between different regression methods. As we gather more samples, the differences in how methods perform become less pronounced, suggesting that the quality of training data plays a crucial role in regression outcomes.